Bismillahirrahmanirrahim, lecture number 12A, and we will be talking about the internal combustion engine based on the Otto cycle, and briefly we'll be discussing also the diesel cycle. In our last lecture, we did said something about the ideal heat engine cycle based on the corner cycle, based on the corner processes. In that cycle, we did discuss like there are four processes towards the adiabatic process and toward the isothermal processes. And the efficiency of the corner cycle was the maximum efficiency that was possible. But in a corner cycle, we also discussed that the engine based on the corner cycle would be impossible, and that impossibility is due to the heat addition and heat rejection, which is isothermal. So it is very difficult to have heat transfer to the system and keeping the temperature constant, or heat actually rejecting from the system, keeping the temperature constant. So in a real internal combustion engine or a real heat engine, these processes, the heat addition and heat rejection, they are replaced from the isothermal to any other processes. So in Otto cycle, it has been replaced by the heat addition is replaced by the uh, constant volume processes, and in a diesel cycle, the heat addition is replaced by the constant pressure processes, while heat rejection in both cycles are at constant volume processes. So based on that one, we will be talking about the Otto cycle and diesel cycle. The Otto cycle is actually a set of processes that is used by the spark ignition engine or the SI engine, while the diesel cycle is the processes which actually is used by the CI engine or the compression ignition engine. You might have got a little bit knowledge about the two-stroke engine and the four-stroke engine. Uh, the stroke is actually the displacement of the piston from the top dead center to the bottom dead center. The top dead center is the minimum volume, I would say, like it is near the piston head, while the dead center is the maximum volume that the piston can move. We have got this volume known as the clearance volume, while the whole volume, this volume is called as the swept volume, while this is actually called as the whole volume or the total volume. So we have got the clearance volume, the swept volume, and clearance plus swept volume is what we call it as a total volume. So in a four-stroke engine, we have got the four stroke from the top dead center to the bottom dead center and bottom dead center to the top dead center. We have got the intake stroke, we have got the compression stroke, we have got the power stroke, and we have got the exhaust stroke. While we have got four processes in it, and briefly we will be discussing these four processes. So what we have got the intake stroke. So intake stroke is when the air and fuel mixture in an SI engine is withdrawn from the outside. So at, let's say, at state number 5, we have got the we can start the our intake stroke. So at state number 5, the intake valve would be open. Once the intake valve is open, the gasoline vapor and the air mixture would be drawn into the cylinder. So it will be drawn from top dead center to the bottom dead center. So the whole piston will move from the top dead center to the bottom dead center. Once it reach at the bottom dead center, the intake valve would be closed, and we will be starting the compression then. So compression would be actually from state 1 to state 2, and which we call it as the compression stroke. So in compression stroke, the pressure increases and also the temperature increases. This is what we call it as the adiabatic compression. We would not actually assume like the heat would be either losing the system will be either gaining heat from the outside or losing heat to the outside. So the process is adiabatic compression. Once we reach at state number 2, there would be actually a spark ignition into state number 2. So once we ignite, or once the spark is ignited, the fuel and air will be combusted and heat will be transferred from the fuel to the cylinder. So from 2 to 3, the heat is transferred from the fuel to the heat is or the fuel is combusted, and heat is absorbed from the or the heat is transferred, sorry, to the cylinder. So from 2 to 3 there will be heat transfer. The heat transfer is at the constant volume. So from 2 to 3 there will be constant volume heat addition. So if you go to the first law of thermodynamics. So change in heat, that would be equal to the change in internal energy plus the work done. So if the work done is zero, as we have got the constant volume, so whatever the heat is transferred will be used to change in the internal energy of the system. So from 2 to 3, the heat is transferred to change the internal energy in the system. Now at state number 3, we have got the high pressure also, we have got the high energy also. Now we have got the power stroke. The power in a power stroke, the piston will actually would be pushed from top dead center to the bottom dead center. So it is what we call it as the power stroke, and it is what we have got the adiabatic expansion. So adiabatic expansion in which the work would be done by the system on the surrounding. If I would say like the work would be transferred, or the work would be from the piston to the crankshaft. So we have got the power stroke from 3 to 4, and that is what we call it as the adiabatic expansion. Once we reach at 4, the exhaust valve would be open and the gas would be leaving the system. So when the gas is leaving the system, actually we have got the heat transfer which is out of the system, and again if the it is the constant volume heat rejection, so again the internal energy would be reduced, the temperature would be dropped. We have reached at state number 1, in which actually heat rejected reservoir at temperature T from T4 to T1. Once we reach at state 1, the exhaust valve would be open and the piston will move the remaining combustion product out of the chamber. So from 1 to 5 actually there would be an exhaust stroke. So we have got 4 stroke, the intake stroke from 5 to 1, the compression stroke from 1 to 2, then we have got the combustion, then we have got the exhaust stroke, the power stroke from 3 to 4, in which we getting the power out of the system, then we have got the heat transferred out of the system, and then we have got the exhaust stroke from 1 to 5. 4 processes. From 1 to 2 we have got the adiabatic compression, from 2 to 3 we have got the constant volume heat addition, from 3 to 4 we have got the adiabatic expansion, and from 4 to 1 we have got the constant volume heat rejection. So down there you can check like there would be intake stroke, in which the piston would be moving from top dead center to the bottom dead center. Then we have got the so the piston will be moving from this one. Then we have got the compression stroke, in which the piston will be moving from the bottom dead center to the top dead center by keeping the both valve closed. Then we have got the combustion, and when the combustion is complete, we will be having the power stroke, which will be from the top dead center to the bottom dead center, and then we have got the exhaust stroke, which actually any residual which is remaining inside the combustion chamber, it will be moving outside. This is what we have got the ideal Otto cycle, and but based on the actual cycle, the actual cycle does not have got that sharp transition due to the opening and closing of the wall, due to also the we have also assumed like at from 2 to 3 there would be a constant volume process, while if you can imagine the piston move too fastly, so if it is fastly then we can actually say like the piston will be moving up, and obviously at the same time it will be moving down. So we do not have got that sharp constant volume process. Also we do not have got that sharp constant volume heat rejection. Also the closing and the opening of the valve would actually also have these thing the curve which is not so sharp, and it will be actually a little bit curvy. So the ideal um, Auto cycle look like this one, but in actual cycle it will be not so this one, and it will be actually a little bit not sharp transition between the different processes. The efficiency of the Otto cycle, the starting point again for the efficiency of the Otto cycle is the work by the system divided by the heat input. So we have got the work which is actually the work done would be equal to the change in heat QH minus QL and divided by the heat maximum heat would be equal to the maximum efficiency. So that would be H. If you can look at this one, so this will be 1 minus QL by QH over here. Now, simplifying this thing, if you can check it over here, the QH is from 2 to 3, which is the constant volume heat addition. And I've already said like the constant volume heat addition would be at once we have got a constant volume heat addition, the heat would be the converted to internal energy only. So QH would be equal to change in the internal energy. And for the ideal gas or for the air, I would say like the internal energy would be equal to CV delta T. So QH from 2 to 3 would be equal to CV delta T, and that is actually CV T3 minus T2. Now going towards the sorry, not integral side again because we have already done the C T2 T3 minus T2. Again for the heat rejection, there would be heat rejection from 4 to 1 and CV T1 minus T4 would be there. Putting them to value in here, so efficiency would be equal to 1 minus T4 minus T1 divided by T3 minus T2. Simplify again, we have got another two processes. The process is from 1 to 2. We have got the adiabatic compression, and the process is from 2 to from 3 to 4. We have got the adiabatic expansion. So from 1 to 2, that would be equal to, if I would say like for the adiabatic process, T1 V1 raised to power gamma minus 1 would equal to T2 V2 gamma minus 1. As T1 is also equal to T4 and also T3 is also equal to, sorry, T2 is also equal to T3. So it will be something roughly like this. And then similarly, it will be for the, it is for the expansion and this is for the compression. So just subtracting this equation from this equation, we will be getting equation something like this. And dividing again, simplify again, T4 minus T1 divided by T3 minus T2 would be equal to V2 divided by V1 gamma minus 1. So this is simplifying again the above equation. So now our efficiency would be equal to 1 minus V2 by V1 gamma minus 1, something like this. Um, Now the quantity V1 by V2 is equal to R, and obviously this is what we call it as the compression ratio. It is the ratio from, actually this is the moving from the top dead center to the bottom dead center, or the bottom dead center to the top dead center. In terms of compression ratio, the efficiency of the Otto cycle would be equal to 1 minus, as we have said over here. So that would be 1 minus 1 over R gamma minus 1, keeping the view like it is actually now V1 by V2 over here. The ideal Otto cycle efficiency is shown as a function of the compression ratio in this graph. As the compression ratio increases, the Otto cycle efficiency increase. But as we have already said, like we have already seen, like uh, once we are doing the compression, the pressure is also increasing and the temperature also increasing. So if the temperature is too high, the mixture will ignite without the spark, and this is what we do not actually want to do. This is what it is, the problem of the knocking, if you can imagine. Normally different engine are compared with a non-dimensional dimensional work ratio. It is the ratio of the work done divided by the enthalpy flux. This is often desired to increase this quantity because it means like the smaller engine for the same power. So if we are increasing this ratio, that means like the smaller engine will be giving us the more power. Simplifying the above equation, power would be equal to W would be efficiency. As efficiency, we have got the work done divided by the heat transfer from 2 to 3. The work done, so from power W would be equal to the efficiency multiplied by, sorry, multiplied by the heat transfer from 2 to 3. Sorry, 2 to 3, and that is work done. Enthalpy flux is actually mass of the fuel multiplied by the enthalpy change. So the heat transfer from 2 to 3 is actually equal to the mass of the fuel burn multiplied that by the enthalpy or the heat of the reaction, which is actually from the combustion of the fuel. This is the chemical energy liberated per unit mass of the fuel now, where m dot fuel is the fuel mass flow rate. The non-dimension power is equal to, putting them value would be equal to something like this. The quantity in this equation, if we are looking at the tachymetric ratio, so mass of the fuel divided by the mass m dot is equal to 1 over 15. That means like the for the 1 kg of fuel, we need actually 15 kg of air. So this is what actually we have to put in this equation, and coming up we have got this ratio, non-dimensional ratio. So increasing this ratio would mean like the smaller engine having the more power. Now briefly discussing the diesel cycle. The diesel cycle is the compression ignition cycle rather than the spark ignition cycle. In diesel cycle, the intake stroke from the top dead center to the bottom dead center is not the air and fuel mixture, but it is the air only. So in intake stroke, in the last we said something about like state number 5, let's say. So intake stroke from 5 to 1 would be air only. Then we have got the adiabatic compression, or what we call it as the compression stroke, from 1 to 2, in which the air only would be compressed from 1 to 2. Now, once we have reached at stage number 2, as the air, if I would say like as the air is highly compressible, so we have got at stage number 2, the pressure would be higher and the temperature would be higher as well. Once we reach at state number 2, we have got high pressure and high temperature. And then at state number 2, the fuel is injected in a combustion chamber, or if I would say like in a cylinder. So once the fuel is injected, there would be some auto ignition, and when the fuel is combusted, we would keep the pressure constant while keeping that high pressure constant. So from 2 to 3, it will be actually the heat addition, I would say, in other words, heat addition or the combustion at a constant pressure process. Uh, we would supply the fuel till state number 3, and then we will be having the cutoff fuel, or what we call it as a cutoff volume. V3 is what we call it as a cutoff volume. So at state number 3, we will cut off the fuel, and then there would be actually the power stroke from 3 to 4. And then obviously similarly there at number 4 there would be exhaust valve open, in which the gas would be actually taken out, and there will be heat transferred out of the system, and that is actually constant volume heat rejection. And similarly from 1 to 5 there will be the exhaust stroke, in which the combustion residual which is inside the cylinder will be taken out of the system. So same thing we have discussed in the Otto cycle, but over here in the diesel cycle, the heat is transferred to the system by not in a constant volume process, but in a constant pressure process. So state 1 to 2 would be adiabatic compression. State 2 to 3 would be constant pressure heat addition. 3 to 4 would be adiabatic expansion, and 4 to 1 would be constant volume heat rejection. So idealized heat engine, we can imagine in a figure 12.5. Thermal efficiency, we have done in the last slide as well. So that will be 1 minus QL by QH. Now the QH is not constant volume process, but is a constant pressure process. So heat, in the last lectures, we already said like heat transfer in a constant pressure process equal to change in enthalpy when we were doing the first law of thermodynamics. So that would be equal to Cp delta T over here, and Cp delta T is from 2 to 3, so that would be Cp T3 minus T4. Uh, this cycle can operate with a higher compression ratio, as earlier said, like the Otto cycle actually combust the compress the air and fuel mixture, while the diesel cycle only compress the air. So the air is highly compressible than the air and fuel mixture. So we have got the high compression ratio in the diesel cycle. Um, with a higher compression ratio than the Otto cycle, because only air is compressed and there is no risk of auto ignition of the fuel. Although for the given compression ratio, if I'm say like the Otto cycle has got the higher efficiency, because the diesel engine can operate at the higher compression ratio, the engine can actually have the higher efficiency than the Otto cycle. Otto cycle will be having same efficiency of, if I would say like the higher efficiency than the diesel cycle, if we are running in the same compression ratio. But obviously it is not possible for the Otto cycle to be run on the same compression ratio, as there is a chances of the auto ignition of the air and fuel mixture. So obviously a diesel engine have got the higher efficiency than the Otto cycle. I hope like you understand this internal combustion inside cycle, if in other word, the real heat engine cycle. If you have got the any question, you can post it in your Google Classroom, or if you are subscribing the YouTube channel, you can actually tell me in the comment section, and then I would be able to answer that. Have a nice time.